So now we want to solve the part B of this question. So the part B is that it is proposed to balance this system by adding masses to pulleys A and C. So now we are adding two balancing masses at location A and location C. So determine the required masses and their angular position relative to MA. So we need to calculate the masses and their relative position, which is their angles with respect to the MA. Okay, now already we have masses at A and C, which are out of balance masses. So in addition to these out of balance masses, now we will also add balancing masses to location A and C. So if you try to draw the free body diagram of this case, so it should look like this. That you have this shop, and at location A, we have a force which is in this direction, FA. The FB is is in this direction here, and FC is in this direction, as you can see from this figure here. So that is the FC is in the downward direction, and we can also take the so now in addition to these three forces, we will add another uh, RC, and we will also add RA. So this RA and RC is the reaction forces of the balancing masses that we will be adding to the system here. So these are that is what we want to calculate here. So in addition to FA and FC, now we also have RA and RC here, and this will be the required balancing masses that we would like to calculate here. So to calculate this RA and RC, we will follow the similar procedure that we did in the previous example. So here, as we know that for dynamic balancing, we have these three conditions: that summation of all the forces, all the moments at A equals 0, and summation of all the moments at C equals 0, and then summation of all the forces equals 0. So we have these three conditions here. So we can either use A or condition 1 and condition 3, or condition 2 and condition 3 here. So we just use the condition 1, that is summation of all the moments, summation of all the moments at A equals 0. Okay, so if we use this condition here, and again we can assume that this is our positive positive moments in the counterclockwise direction. So if you look at the location A is here. So if you take moments from A, so because if you add these two additional forces to A and C, so the reaction at D and E will disappear because the system will be in total dynamic balancing. So there will be no reaction at D and E. Therefore, we cannot include forces at D and E because the system will be dynamically stable, dynamically balanced. So as you can see here, that if we take moments from A, so we have these three forces. One is FB, one is RC, and one is FC. And now we know the distances there, so we can calculate the moments. And we can see here that if we take the moments here for the FB, so for the FB, it's going to be in this direction here. So the FB times times the dB. So we know that it's in this direction here, in the direction of the force. So it's and we know that this angle is 60 degrees, so this angle is going to be 30 degree, and this this FB times dB. So FB in this case is this force here, which is 438.6. And we will multiply this with the distance from A. So the distance from A is in this case is 600 millimeter, which is 0.6 meter here. So this will provide you with 263.2 Newton meter. And now, as you're going to see in this case, that you have this moments here. So similar to the previous case, we will now split this into two components, into X and Y. So the X component will be this 263.2 into cos of 30, and this will provide you with value of 227.9 Newton. And we will also have the Y component, which will be 263.2 sine of 30 degree, and this will be 131.6 Newton. So we will get the X component and the Y component of this this vector here. Now, in addition to this, now we can calculate the the moments, the moment which is due to the FC, which is the FC is this this force here, and if we know that this this will be in this negative direction here. So, and the value of this, because this angle is 210, and then this angle will be 60 degrees, and it is in the direction of this this MC, and this will be equal to FC times DC, so into the distance. And as you can see here, the this force is 219.3, and the distance here is from A to C, which is this distance here, which is 1.5. And from here you can get the value, which is 329.0 Newton meter. Okay, so if you calculate this value, you may think that because the FC is in the downward direction, so this should be negative. And we will include this because you can see the vector is in the negative direction, so obviously its X and Y components are automatically negative. So if you take its X component, the X component of this 329 is minus, because it's in this direction here. So if you find out its component, X component is in this direction and Y component is in this direction. Now for this force, the X component was in this direction and the Y was in this direction, so both were positive because this vector was positive. So you can also say that this is our negative vector. That's why its X and Y components are negative. Okay, so the X component is 329 cos of 60 degrees. So it will provide you with value of minus 164.5 Newton meter, and the Y component will be minus 329 sine of 60, which is going to be minus 284.9 Newton meter. Now, in addition to this, now we have this additional force here, and this additional force is RC. We don't know that that if it is positive or negative. But if you look at the figure here, so we are assuming that it is maybe in this direction here. So the mass that you will be attaching at location C, so this is, you can say, is MCRC. So the force is going to be in this direction here. So the FC is going to be in this direction. We are assuming it here. Uh, it's just our assumption. If you do all the calculation will give you the exact value of MC and RC, and it should also provide you with the exact direction of it. So in this case, we are assuming that it's just a positive moment, and obviously we are taking the moment. So the moment will be equal to RC times the this distance here, which is 1.5. And this will be our angle here. So we can call this angle, for example, alpha C, and this value will be equal to AC times RC. So AC RC is the whole vector, and we are taking it positive. And obviously now, similar to the previous cases, we need to split this into two components, into the X and Y component. So X component is also positive and the Y component is positive. So this is our assumed direction. So if you calculate the X direction of it, so that will be equal to AC RC cos of alpha C, and the Y component will be equal to AC RC sine of alpha C. So now we have all the information that we need for applying this condition here. So now we can apply the condition, and we will calculate the values of the this RC and AC, because we know AC, which is 1.5 in this case. Okay. So now what I will be doing, I will be just applying this condition, summation of all the moment at A equals 0, and I will be applying the initially it in the X direction. So we have all the X component 1, component 2, component 3, and then we will just add all these components together. So you can see, you can say AC RC cos alpha C, and then you have so this is the X component of this final vector of the FC. And then you have the this component here, which is 227.9, and which is positive 227.9. And then you have this X component which is negative minus 164.5. So equal to 0 here. So now in this equation, because we know AC, so AC is the distance from A to C, which is 1.5. So from this equation, now we can calculate this this RCX. So this RC cos alpha C, you can call this RCX. So from this equation, you can calculate RC cos alpha C, which you can call it RCX. So you will get this thing, which will be equal to minus 42.3 Newton. So we managed to calculate RCX. Now we will apply a similar condition about the y-axis. So if we apply this summation of all the moment at A equals 0 about the y-axis, so what we will do, that we will again just use this thing. So AC and RC sine alpha C, and the one Y component is here, which is 131.6, and it is positive. So plus 131.6 The next y component is negative, which is minus 284.9. So equal to 0, and from here we can calculate RC sine alpha c, and you can call that this component is RCY, because this is the y component of this reaction. So this will provide you with a value of 102.2 Newton. Okay, so if you calculate these two values, now even you can draw this vector here. So this is our coordinate system x and y. So but you can see here that in this case RCX is negative, so this means that you are going in the negative x direction, which is minus R42.3 in the negative x direction, and then you are going 102.2 in the positive y direction. So you are coming here and then you are going here. So this value is 102.2, and now the final vector, which is our RC, is this vector here. So RC is the resultant of these two, which we can calculate by using this equation here. So RC will be equal to RCX square plus RCY square under the root. So this will provide you with the value of the RC. So the RC will become 110.6 Newton. Okay, so if you calculate this thing here, now you also need to calculate this this angle here, and you can, for example, call this angle maybe alpha c dot c dash, because the actual angle was relative to this MA. We want to calculate the angle relative to MA, and this alpha c is just this angle here. So if you want to calculate this angle here, alpha c dash, this will be equal to tangent inverse 102.2 divided by 42.3. So the angle here will be 67.5. And now if you want to find out the angle relative to position of MA, so MA is in the vertical direction here. This means that you are actually required to find this angle here. So you want to calculate this angle here. So this means that if you add 290 plus 290 plus 290 and plus alpha c dash, so this will be our required angle. So the required angle, which is you can call is theta c. This will be equal to 270 plus 67.5. So which will be equal to 337.5 degrees. So here you manage to calculate the value of this theta c, and now the RC in this case is 110 Newton. But we now want to calculate the MR value of this this reaction here. So the MR value can be calculated from this reaction. So as you know, the MR value from these equations, that if you are given this RC, so RC means that is MC RC omega square equal to which is the value that we calculated here, which is 110.6 Newton. So from here you can calculate MCRC, which will be equal to 110.6 divided by omega square, and you know the value of the omega square, which we 110.6 and divided by which was 1000, but you need to convert this into radian per second, so you will multiply with 2 pi divided by 60, and this will be square, and from here then you will get a value of 0.01 kilogram meter. So we managed to calculate the MCRC at location C, which was one of the requirement. Now the second requirement is that we now want to calculate similar value at location A, that is RA. So for RA, as we explained earlier, you can either use this condition, summation of all the moment at C equal to 0. So you will need to calculate all the moments. On the other hand, you can use the condition that is summation of all the forces equal to 0. So we will use this condition here, that summation of all the forces equal to 0. So obviously we will use the forces in x direction and y direction. So this is our forces, so FA, FB, FC, and we have the values which we calculated in the previous part, and we also calculated its x and y components of these forces, which you can calculate from the diagram. Okay, now we we also managed to calculate this reaction force, which was RC, and we also know the component, the x and y component of this reaction force. So now we have all the information. Now we can apply this condition here. So we will apply this condition in the x direction first. So if you apply the condition in the x direction, so now in addition to these four forces, so which is FA, FB, FC, and RC. Now you also have this RA. So you have actually 5 forces now. And if you apply this condition here, so this will provide you with the RAX. And when you apply the condition in y direction, that will provide you with the RAY. Okay, so and obviously again we are assuming that the FA is again in the first quadrant. We are assuming that this is MA and this is RA in the first quadrant, similar to the previous case that we assumed everything in the first quadrant. And then from the actual calculation, we found that it's actually in the second quadrant, because this was negative and this was positive. So again, this is our assumption here. Okay, so if we apply this summation of all the forces in x direction here, so we know that we can split this into two components. One is FAX and one will be FAY. So this is our FAY. So our RAX, RAY, you can call it. So you can call this RAX and RAY. So if you start with this RAX, so this is the first force in x direction, and now you have in addition to this, now you have this force and this one and this one. So you have these forces here in the x direction, so 0, and then you have the component of FB, which is 379.9, and then component of FC, which is minus 109.7. And in addition to this, you will also add this condition here, this force here, which is minus 42.3 and equal to 0. So from here you will calculate RAX, which is equal to minus 227.9 Newton. And similarly, you will apply the same condition in the y direction here. In the y direction, you will have RAY, which is this force here, which will be due to uh, balancing mass that you will add to A. And now you have RAY, and in addition to RAY, you have these three forces here and one force here. So which is 329 positive. Then you have 219.3, and then you have minus 189.9. So we will just add all these forces in the y direction together, and we will also add this force to the system here, which is RCY, so 102.2 equal to 0. So from this equation we can calculate RAY, so which will be equal to minus 460.6 Newton. So if you calculate this RAX and RAY, now if you see here, here we assume that RAX and RAY both are positive, but the actual calculation provided us with the negative values. So this means that the assumption that we did was wrong, and the actual directions are in the opposite direction. So if you draw the actual RA here, so the RA is in this direction here. So as you can see, the RA is here, so it's 227.9, and this is in the negative x direction, and again this is negative, so which is in this direction here. So 460.6 here, and then the resultant force is in this direction, which is our RA. So RA is in the third quadrant now, and we can calculate RA, which is simply RAX square plus RAY square under the root. So this will be a value of 513.9 Newton. And we can calculate this angle here. So if you call alpha A dash this angle, so alpha A dash is equal to tangent inverse and 460.6 divided by 227.9. So just the perpendicular divided by the base, and this will provide you with the value of 63.7 degrees. But in the question, we were asked to calculate the values with respect to this the mass A, and the mass A was in the vertical direction. So you need to calculate this angle here. So this is our theta A. So theta A in this case will be equal to, so as you can see in this figure, it is 90, 90, 90, and minus this alpha A. So this means that 270 minus alpha A dash is our theta A, the required angle. So which will be 206.3 degrees. And we calculated this RA, and we know that RA is nothing but it's just so our RA is MA RA omega square, and this MARA is not the same as this value here, because it was the given value, but this is now, in addition to this, we now adding another values here. So it's better to call this maybe MA dash or A dash, and similarly call this MC dash RC dash. This will this is given is 513.9, and if you want to calculate MA dash or A dash, so you will divide this 513.9 divided by omega square, and this will be equal to 0.047 kilogram meter. So by using these equations, you will calculate the MARA, its angle, and similarly MCRC and its angle here.